Welcome, class. In this video, I want to look at a problem where we are going to calculate the pH of a weak acid strong base titration at several points along the way. So our problem is given here as a 40 milliliter sample of HNO2, right, a weak acid, nitrous acid, is titrated with a 0.200 molar potassium hydroxide solution, a strong base. Now, the first question that's asked here is, what volume of KOH is needed to reach the equivalence point? Okay, so this is sort of a common thing that we often want to look at, and the basic premise here is at the equivalence point, the moles of HNO2 will equal the moles of KOH added. Okay. So and I forgot to add in the problem here. This is a 0.100 molar HNO2 concentration. Okay. So if we start off at one of these, right? So we have to start with the acid here because we know both the volume that we've used and the concentration. So the moles of HNO2, right, are going to simply be the molarity of HNO2 times the liters of HNO2 used. So my molarity is 0.100 molar, or moles per liter, times 40 milliliters, but in units of liters. And I'm going to get 4.00 times 10 to the negative third moles of HNO2. And so that tells me that I must also have 4.00 times 10 to the minus 3 moles of KOH at the equivalence point. Now, since now I know moles and I know the concentration, if I take the moles divided by the concentration, or we'll write it like this, times 0.200 moles per liter, right? That's my molarity. That's going to equal, my moles cancel, and so we're going to get a volume of 0.0200 liters, or 20 milliliters. I guess if we write this out correctly, right, it would be 20.0 milliliters, the right significant figures. So it's going to take 20 milliliters to get to the equivalence point here. Okay, so we have that piece of information. That's just sometimes a question that's asked. So now let's turn our attention to the pHs. So the first one is the initial pH. So I'm just going to show here that we're going to do the initial pH. So remember, the initial pH is just simply a weak acid ionization. Okay. So, if we have a weak acid ionization, the way we're going to do that is we're going to set up our weak acid equilibrium. So I have to be able to write out my weak acid plus water in equilibrium with the conjugate base plus hydronium ion. Now, we can look up, and the Ka of HNO2 is going to be 4.6 times 10 to the negative fourth. So if we set up our ice table, that we have our initial concentration here of 0.100 molar and 0 and 0. Our change is going to be 0.1 minus x, x and x. I'm sorry, it's going to be got all ahead of myself there. So it's just going to be minus x. And so the equilibrium concentration is going to be x and x plus x. So if we then go to solve this, we get our Ka 4.6 times 10 to the negative fourth is equal to x times x over 0.1 minus x. Now we are going to do the x, a small constant, the x small approximation. So we get 4.6 times 10 to the negative 4 is equal to x squared over 0.1. So if we do our math, we get x is equal to 6.78 times 10 to the minus third equals x. Now, so I'm going to shift to another page here, need a little more space. So x is equal to 6.78 times 10 to the minus third. From our ice table, we know that the concentration of hydronium is equal to x. So it's equal to 6.78 times 10 to the negative third. And the pH will be equal to the negative log of 6.78 times 10 to the minus third. And so the pH will equal 2.17 initially. Okay, so that's the initial pH. All right, so we saw how to solve for the pH of the initial weak acid. Okay, so now let's move into the titration itself, and let's solve for the pH after we've added 5 milliliters of KOH, our strong base. So remember when we were talking about this, right? At this point during the titration, we're setting up a buffer system, right? We are, as we add sodium hydroxide, we are, or in this case potassium hydroxide, we are converting our weak acid to the conjugate base. So we're setting up a solution where we have both our weak acid and our conjugate base. Now, remember when we talked about we have to deal with this, we're going to have to deal with this in 2 steps, right? we're going to have to, first, we have to figure out how we've changed the concentrations of our weak acid and our conjugate base. So we have to look at how many moles of base we've added, and then that'll tell us how many moles of conjugate acid we've created and how many moles of acid we've lost. So the basic idea is we need to do a stoichiometry problem. So after 5 milliliters, right, we have added, if we look at the math here, we've added 0.5 times 10 to the minus third liters. And remember from our problem, flip back, our potassium hydroxide is 0.2 molar. So if we do our volume times our concentration, turns out we've added 1 times 10 to the minus third moles of hydroxide. Now, if we set up a little table here, and so before the addition, right, we added, 0 moles of hydroxide so far. So we had 4 times 10 to the minus third moles of our weak acid. Now, that number, remember, is coming from the first part of the problem. When we solved for the volume at the equivalence point, part of that was calculating how many moles of acid we had in our original solution, our 40 milliliters of 0.1 molar. So this is how many moles of acid we have at the beginning, and of course we don't have any conjugate base. So we add this 0.001 moles of hydroxide, and that's going to cause, right, since we're adding base, right, it's going to cause the acid part of our buffer to react, right? So we're going to lose that many moles of acid, and we're going to generate that many moles of our conjugate base. And so we end up at the end, of course, we've used up our hydroxide, and at the end, we end up with 3 times 10 to the minus 3 moles of our acid and 1 times 10 to the minus third moles of our conjugate base. Now, this gives me my starting solution, right? Or my solution after the addition. So how do I calculate the pH of that solution? Well, for a buffer solution, we can use something called the Henderson-Hasselbalch Equation, which we'll go into more in the buffer section, but it's this solution, or this calculation, where the pH is equal to the pKa plus the log of the conjugate acid, or conjugate base, over the acid concentration. Now, a little shortcut here. So right here we have moles, right? Now, this is not molarity, right? So this equation calls for molarity. Now, what we have to remember is we can convert these into molarity, right? And the way we would do that, if you wanted to do it, would be to divide these by the volume of our solution. So if I wanted to do that, I would divide each of these by my volume. In this case, the volume would be 45 milliliters, my original 40 milliliters of acid, plus the 5 milliliters of base that I've added. So I have 45 milliliters in volume. So I would divide each of these by 0.045 liters. And that would allow me to calculate the molarity. But if we notice, right, because in this equation it's a ratio, right? It's a ratio of the conjugate base to the acid, right? The ratio is not going to change because we're dividing by the same volume here. So if you want to save yourself a little time here, we can just use the moles, right? It's going to give us the same ratio. Now, another thing to sort of comment on is the reaction that's taking place here. So we're adding the hydroxide ion. It is reacting with the acid, and we are generating water plus our conjugate base. Right, so we can understand that, the same amount of acid that reacts, we're going to generate that same number of moles of our conjugate base. So that's why these go up and down by how many moles of base we've added, right? Or because everything's a 1-to-1-to-1 stoichiometry. So if we go ahead and solve this problem, so we have the pH. Now, remember the pKa, right? So the pKa is the negative log of the Ka of our acid. So remember the Ka, we looked it up, look back, it was 4.6 times 10 to the minus 4. And that equals 3.34, right? Okay. Plus the log of the conjugate base. So that is 1 times 10 to the minus 3 over the acid, 3 times 10 to the minus 3. So if I work all that out, I get, and I'm going to shift it over here, the pH equals 3.34 plus a minus 0.48, or 3.34 minus 0.48, or a pH that is equal to 2.86. So after we've added this 5 milliliters, we can see that the pH, right, is starting to creep up a little bit, right? We're getting rid of some of the moles of acid, adding in moles of conjugate base, right, which is going to, allow that pH to start to creep up a little bit. And we could go through and do 10 milliliters, 15, etc., up until we get to the equivalence point. But we're all going to do them the same way, right? We're just going to keep changing the moles, calculating the new pH, right, as we go. But let's skip ahead and do the last part of the problem, which is to calculate the pH at the equivalence point. Now, so at the equivalence point, the big thing here is that the moles of base added equals the moles of acid. Now, we've already calculated, right, from our original problem that we had 4 times 10 to the minus 3rd moles of HNO2. So that means at the equivalence point, we have 4 times 10 to the minus 3rd moles of base added, right? Okay. So we've completely neutralized or converted. So we've completely neutralized our acid by the reaction, right? OH minus plus HNO2, HNO2, water plus NO2 minus. So remember, in order to find the pH at the equivalence point, we can think about what kind of solution it is. So at the equivalence point, right, we have neutralized all of the acid, right, with our added base. And so the only species in solution, right, that can affect the pH is the conjugate base of our acid, right, which is a weak base. So we're going to solve this like a conjugate base equilibrium. And so we're simply going to set up an ice table, right, based on the ionization of our weak base. Like that. Now, so we're going to set up our ice table. So our initial concentration of NO2 minus, right, is we have 4 times 10 to the minus third moles, right? Because this is how many moles of acid we had, and all of that acid would have been converted here. Now, to get that in terms of a concentration, right, we're going to divide by our volume. So our concentration of NO2 minus is going to be our moles. Right? 4 times 10 to the minus third divided by our total volume. Now, remember in the first part of the problem, we said that it was going to take, we solved that it's going to take 20 milliliters to get to the equivalence point. We started with 40 milliliters of acid, so our total volume is going to be 60 milliliters or 0.06 liters. So if we do the math, the concentration of NO2 minus at the beginning is going to be 6.67 times 10 to the minus 2 molar. So we're going to fill that in here, and I'm just going to write it like this, just to avoid those decimals, or scientific notation, just to make it a little bit easier. So we're going to start off with none of those, and once this reaches equilibrium, right, this is going to go down by x, these are both going to go up by x, this is going to be 0.0667 minus x, x, and x. So now we can go ahead and go through our calculations. Now, in order to do this conjugate base, we need to, of course, know the Kb of our conjugate base. Now, we don't have the Kb directly, but remember the Ka of our acid is equal to 4.6 times 10 to the negative 4, and we know that Ka times Kb equals Kw, so Kb will equal our Kw, 1 times 10 to the minus 14, divided by our Ka, which is going to equal 2.17 times 10 to the minus 11. So we can now set up our equilibrium expression. Our Kb is equal to our acid times hydroxide over our conjugate, our base. We're going to do the x is small approximation. So this becomes x squared divided by 0.0667. And at this point, again, it's just solving through the algebra. And we should come up to be where X equals 1.20 times 10 to the minus 6th. Now, we already know, if we go back here, that the hydroxide ion concentration is equal to X. So the hydroxide ion equals 1.2 times 10 to the minus 6th. So there's a couple ways, obviously, we can solve this. I like to do it the hydronium ion equals Kw divided by the hydroxide ion. And so the hydronium is going to equal 8.33 times 10 to the minus 9th. And then we're going to solve for the pH. If we take the negative log of this, the pH will equal 8.08. So the pH at the equivalence point, as expected, is going to be slightly basic, and in that sort of order of magnitude of 8 to 9. All right, so this is the idea of different points during the titration. We can solve for the pH. Whether it's the initial pH, we can treat it like a weak acid ionization. In this case, if it's between the initial and the equivalence point, we can treat it as a buffer solution and do our two-part stoichiometry and then Henderson-Hasselbalch. If it's at the equivalence point, we can do it as a weak base, looking at the conjugate base of our acid. So we do a conjugate base ionization and solve for the pH that way. All right, so that should give you some problems to go on, but remember, these are just the same types of problems we've been doing, just with a little bit of a nuance here or there because they're part of a titration.